All right, welcome to the first lecture of the semester. Today we're going to go over section 1.1, and that's all about functions and their graphs. So hopefully this is going to be review. If not, no worries. So first, what is a function? We can define a function. Usually we call it f, first letter of function, from a set D to a set Y. A function is a rule that assigns a unique element f of x, that's an element of, right? So it's in y, to each x in D. So usually we write this as y equals f of x. So we say y equals f of x. This is not multiplication. So I'm not multiplying f times x. I'm saying there's something that I can plug x into, and then I'll get my y back out. So in a lot of different scenarios, we can call x our independent variable. You might spell a lot of things wrong. I'm not getting a PhD in English. We also call it our input of of f. And y we can call our dependent variable. Right? If x is independent, y depends on x, I'm going to call it my dependent variable. It's also the output. That is not how you spell output. There we go. Output of x at x. So that notation is pretty straightforward, right? And so we also have another definition, or two, right? So domain. It's going to be the collection of all of these x's, right? So we also call it D for short. It's the set of all possible inputs. Domain has its partner in crime, range. We also can call that R for short. And it is the set of all possible outputs. Domain's going to have x's, range is going to have y's. So in calculus, okay, I should probably learn how to spell that word. There we go. We only care about the real numbers. There's something called imaginary numbers and complex numbers. We're not going to get into that. Basically, if you ever remember hearing about I, like the square root of -1. We're not dealing with that. He's not in this. We only care. We'll say deal with. There we go. So how can I find the domain and range of a given function? So let's do some examples. It kind of takes some trial and error and practice, right? Practice makes perfect. So what if we had our function? I also denote that fxn function. We're going to put our domain right here and our range right here. So if I have y equals x squared, I can put any number into x squared. I can put a negative number, I can put 0, I can put a positive number. So we say that the domain is -infinity to infinity. And then my range, what are some possible outputs? I'm dealing with the real numbers here, so if I square a real number, I'm gonna get a positive number back out. So I'm gonna go from 0 to infinity. Here's the tricky part that can make an answer really wrong. I can put 0 in, 0 squared is 0, so that means 0 is included. This hard bracket right here is inclusion. Soft bracket means you're not really necessarily including it. I can't really include infinity or negative infinity since those are not really real numbers. I can't attain those. So what if we do y equals square root of x? Can I just put in any old number into here? No, not really. I can't plug in a negative number. So the lowest thing I can put in is 0, but I can put in any positive number. Again, I need to think about if I'm going to include 0 or not. I am. Square root of 0 is 0, so that makes it a hard bracket. For the range, if I can only put positive numbers in, so the square root of a positive number is still going to be positive. So the range actually is the same as my domain, which is pretty cool. So those are pretty straightforward. So let's do a little trickier one. Space these out right. There we go. Y equals, let's see, the square root of 1 divided by x squared. So we might have to do a little bit of work now. So from earlier, I saw that my square root function, this inside, it's called the radicand, by the way. The radical is the little squiggly box. The radicand is the inside chunk. So if I take just this inside, I know from right here that this needs to be greater than 0. So I know that 1 minus x squared needs to be greater than or equal to 0. So then I can do some algebra. I'm going to add x squared to both sides. So 1 is going to be greater than or equal to x squared. And I'm going to square root. Don't forget that negative numbers can be involved into squares. So I can put in a -1 and square it, and I'll get equal to 1. So that means that x is going to be bounded between 1 and -1. Okay? So I don't need to be in red anymore. That's how I get my domain. I take what I know about this bigger picture and I work it through to find this. So what about my range? So I know that my smallest value of x is going to be -1. So if x equals -1, y equals 1 minus -1 squared 1 minus 1, that's 0, square root of 0 is 0. Well, that's the smallest that y can be because that's the biggest x can be. So I know that the smallest y can be is 0. And I also can see that if x equals 0, y equals 1, square root of 1 minus 0 is just 1. And that's how I can get a 1 right here. Alrighty, so moving on. We're going to talk about the vertical line test. So, remember how we said earlier that a function assigns a unique element? Well, unique means single, like one value. So, since a function assigns a single value, or element, we call f of x to each x no vertical line can intersect. Spelling is hard. Graph of a function more than once. So a pretty common example of this is a circle. So the equation for a circle is x squared plus y squared equals 1. So if I draw my graph, what color should we make graphs? Ooh, purple. Let's do blue. A cute little graph. So if you remember anything from, I don't know what class this is in, geometry. This is a circle with radius 1. So let's call this 1. Circle, circle, circle. Amazing. I am an artiste. Well, we can see that when we do a vertical line at 1/2, I intersected these 2 points. So this is not a function. What if I solve for y? Usually we like equations to be y equals something, right? So I'll have y squared equal to 1 minus x squared, and then I can take the square root of each side, so I'll get y equal to 1, y equal to the square root of 1 minus x squared, and then I also get y equal to the negative square root of 1 minus x squared. Sometimes we write this as like a plus or minus. So something like this, we say plus or minus. And those graphs look like this. So y equals square root of 1 minus x squared. Kinsey, why did you choose all these colors? This is actually just going to be the top hemisphere. And y equals negative 1 minus x squared. and this is just the bottom hemisphere. If I check again, well, my vertical line only intersects one point. So they're both functions. Woohoo! Functions. Okay. So another fun type of function, I'll start on a new page, is the piecewise defined function. See how I split this one graph into two? What if I took two graphs and put them into one? How does that work? So the most common piecewise function, or well-known, I'm not going to say common, let's do well-known. Piecewise function is what? Can you guess it? It's the absolute value function. Right, if I have the absolute value of x, that's going to equal, usually I have this big bracket, and then I write what it's going to equal and where it's going to equal it. So it's going to equal x when x is greater than or equal to 0, right? If I put in positive 2, what's the absolute value of 2? It's 2. It's going to give me negative x when x is below 0. What's the absolute value of negative 1? It's 1. Well, negative 1 times a negative gives me 1. So it takes a positive number and it keeps it positive. It makes the negative number negative. So that's why that little guy exists right there. We can look at some other piecewise functions because there's some there is an important part of it concerning that this has the greater than or equal to part and this does not. So let's look at an example. If I'm given f of x equal to negative x when x is less than 0, x squared when x is greater than 0 and less than or equal to 1, and it's going to be 1 when x is greater than 1. So what's that graph going to look like? Switch to blue because that has become our graph color. So from x is less than 0, it's going to be negative x. So it's going to look just like a little line. Oops, that's not right. Start the origin. And that's going to go on forever. And that's this bit right here. Now the middle one, when it's x squared, so we're going from 0 to 1, that's going to look kind of like that. And then we're going to be 1 moving on. So if you haven't noticed, I kind of forgot a little something. When I draw these little lines, let's do these gray ones. When I have negative x, when x is greater than 0, I'm not including 0. So I would draw an open circle. And then from x squared, from 0 to 1, well, that's already 0, so that fills that hole back in, and it fills in a hole right here as well. X greater than 1, there's going to be an open hole, and then continue on, and so on. So if I have a greater than or equal to or less than or equal to, I'm going to have what we call a closed hole. If I have a greater than or less than, going to have an open hole. So that's kind of what a piecewise function, basics of it, all right? So let's talk about some other fun properties about functions. Ooh, zoom in. So we're going to do some more definitions. So we're going to say let f of x be a function on the interval a and b. It doesn't have to be, this is what we call a closed interval because of those hard brackets. It doesn't have to be, but just some interval with x1 and x2 in it. So our first definition is going to be an increasing function. I think we all know, looking at a graph, what increasing means, but what if we're not given a graph and I don't really know how to graph that function? So an increasing function is when for x1 less than x2, f of x2, f of x1 is going to be less than f of x2. So as I'm moving from left to right, I'm going to be moving up. A decreasing function is for when x1 is still less than x2, but f of x1 is now bigger than f of x2. Alrighty, so that kind of seems a little intuitive, right? Increasing function, I'm going to be going up. Decreasing function, I'm going down. What about even and odd functions? An even function is defined as simple as this. If I have f of negative x, it's going to equal f of x. And an odd function f of negative x is going to equal negative f of x. So those seem kind of not really intuitive in my opinion. So let's look at some examples. So of an even function, a really kind of really good example of even and odd functions are power functions. So like x to some power. So I'm gonna draw my graphs. So let's do y equals x squared, which looks like this, and y equals x cubed, which looks like this. They go off in forever. Alrighty, so I want to see if they're even or odd. So let's plug in each one of them. We see I'm going to plug in negative x. So I'm going to have f of negative x is negative x squared. Well, a negative times a negative, that's just positive. So I get positive x squared. So we'll call that one, oh, I like this dark green, even, because it satisfied this up here. So now what if I plug in f of negative x into x cubed? Well, two of those, that's going to be negative x negative x squared. Well, I know that this is just x squared and that's negative x, so this is going to give me negative x cubed. So that's the negative version of my original, aka negative f of x. So this one is going to be odd. Even and odd functions, you can even look at a graph and kind of tell them apart. Even functions are symmetric about the y-axis. And odd functions are symmetric about the origin. So you can see here the y-axis is this guy right here. And we can easily see that that is pretty symmetric around that gray line. The origin is 0, 0. So if you see right here, if I rotate this, I'm going to get the same exact picture. So the negative version of this is this. Okay? So let's move on to types of functions. One type of function that you guys should be pretty familiar with is a linear function. It kind of gives a hint of what it looks like because it has the word line in it. What is the equation for a line? We say that it's y equals mx plus b. M, we always denote as the slope. B as, we say equal to the slope, the y-intercept. There's also different ways of writing a line. That's a plus right there. Whee. So the y-intercept is going to be b. You can also write this in like, I think it's like slope point form, but I like y equals mx plus b. Has a soft spot in my heart. The next one is a power function. Whoopsies. Power function. That looks like f of x equal to x to the a, where a is a number. We kind of already looked up two power functions, x squared and x cubed. So that's when a is greater than 1. We'll get like x squared, x cubed. Oh, come on. What are you doing? And so on. If a is less than 1, we will get like x to the 1/2. I can just write that as the square root of x. X to the 1/3. Well, that's just going to be the cube root of x. Alrighty? And then our next type of function is going to be polynomials. So you might have been like, wait, I thought a power function was kind of like a polynomial. Close, but there's a little bit of a shift. And we'll get on to shifting functions a little bit. We call polynomial functions like p of x. And I have all these coefficients. I'm going to call them a sub n. I don't know what number it is, just some number, and I'm going to have x raised to some power plus so many more, and then I'm going to end with like some other letter. So if you think of like x squared plus 3x plus 4, that's a polynomial. Example. Okay. Well, what if I took one polynomial and divided it by another polynomial? We call those rational functions. Rational comes from ratio, ratio, I'm going to divide things. When I divide things, that's also called the quotient. Right? So if I have some f of x equal to one polynomial divided by another polynomial. So an example of that is if I had y equal to 11x plus 2, all divided by 2x cubed minus 1. The top one would be p, the bottom one would be q, and so on. So 2 more types of functions, and then we are done. And we can move on to 1.2 and 1.3 for the day. So next type of function is one of my favorites. It is the trig functions. Trigonometric functions. An example of one is f of x equals sine of x. Remember, there's 6 trig functions: sine of x, cosine of x, and tangent of x, and then there's 3 more. Dot, dot, dot. Remember, these are just like how f of x is not multiplication. Sine of x is not multiplying sine times x. I'm not saying sine times x, I'm saying sine of x. I'm putting in a number and I expect a number back out. So if you're trying to solve for like sine of x equal to 0, you cannot x equal to 0 divided by sine. What is that? That doesn't exist. Nope, not a thing. Another fun family of functions are the exponentials. Right, so those are going to look like a to the x. Well, aren't those just power functions? Let's scroll up and compare. I had x raised to the a here, so x raised to a number. Well, here, a is still a number. But now I have a number raised to x. So some fun examples of that are 10 to the x, e to the x, really important one, and so on. These functions are really cool. And I'll show you a fun little picture of them. They're gonna kind of be really small over here, and then right after here, they're gonna get bigger and bigger and bigger. Exponential growth. If you hear people talking about coronavirus right now, how there's exponential growth, it's because we're looking like this. We're getting steeper and steeper and steeper as time goes on. So exponential functions have a fun brother called the logarithmic functions. Logarithms are kind of a little tricky to think about. I had a lot of trouble with them, but they look like log base a of x. So really fun examples of that, log base 10. Oh, what is that? What are you doing? Crazy technology. Log base 10 of x. Also ln of x. That's how I write my ln's. This right here asks the question, if I put x into here, so if I have like 2, it's asking what can I raise a to get to x, and that's my answer. If you want to think about it, it's an exponent. So if I have log base a of b, that's going to equal, oh my god, Mackenzie, can you spell to save your life? Probably not. what power to raise A2, so A question mark equals B. All right, so those family of functions also look pretty similar. They only can give you positive outputs, and they start really close to the axes, and then they go up like that. And they go off forever. So those are logarithmic functions. I can't plug in a negative number into right here. Why? Remember, like x2 squared? I can't plug in... Wait, what am I trying to say? Oh yeah, so basically I can't plug in, I did this backwards. So if I had 2 and I want to make it equal to -1, I can't raise that to any power to equal -1. Doesn't work. So that's why this is only on the range is only going to be 0 to infinity. And I can never actually hit 0. I can't raise anything to the power to get to 0. So, fun thing about that. Alrighty, so I think that's going to finish 1.1. And then we will continue on to 1.2.